SpaceX just confirmed what the rest of the rocket industry has been dreading. Starship is getting landing legs. It is going to land on drone ships in the ocean, and when it does, every other rocket company on the planet will officially have no answer. Mechazilla, the giant mechanical catching arms on the Starbase launch tower, was already one of the most audacious engineering achievements in spaceflight history. The idea of catching a 230-foot, 200-metric-ton rocket booster in midair with a pair of tower arms seemed impossible until SpaceX did it on Flight 5 in October 2024, and then did it again and again. 3 successful booster catches in the span of a few months made Mechazilla feel almost routine, but here's the problem. SpaceX identified the moment Mechazilla started working reliably. It only works if the rocket comes back to the launch tower, and not every mission allows that. So SpaceX is now developing deployable landing legs for Starship. FAA documents and SpaceX planning materials confirm that Droneship landings for Starship are expected to begin in the second half of 2026, and the implications for the entire rocket industry are enormous. To understand why landing legs on Starship matter so much, you need to understand the fundamental operational difference between Mechazilla landings and Droneship landings. When a Starship booster catches on Mechazilla, it returns to the exact launch site it left from. This is ideal for missions where the flight profile allows a direct return trajectory, where the booster has enough fuel after stage separation to flip around, perform a boost back burn toward the launch site, and guide itself back to the tower. But when a mission requires maximum performance, heavier payloads, higher orbits, steeper trajectories, the booster does not have enough fuel to return to the launch site. It needs to land downrange on a drone ship instead, where the ocean platform sits along the flight path and the booster lands without a fuel-consuming boost back burn. SpaceX has performed over 400 Falcon 9 drone ship landings across its Atlantic and Pacific ships. That operational model is mature, proven, and reliable. The challenge now is scaling it to Starship, a vehicle that makes the Falcon 9 look small by comparison. Starship is physically enormous compared to Falcon 9. The Super Heavy booster stands approximately 230 feet tall and weighs over 200 metric tons empty. A drone ship large enough to receive Super Heavy must be significantly larger than the ships SpaceX uses for Falcon 9, currently about 300 feet long and 170 feet wide. The acoustic and thermal environment of a Super Heavy landing burn is radically more intense than the single-engine landing of a Falcon 9 first stage. 33 Raptor engines performing a landing burn above a ship's deck creates an entirely different engineering problem than one Merlin engine doing the same thing. The ship must survive repeated exposure to that exhaust environment without structural damage to its deck, propulsion systems, or recovery hardware. SpaceX is building new, larger drone ships specifically for Starship operations. With reinforced deck plating, improved dynamic positioning systems, and enhanced fire suppression capability, these ships must also be capable of operating in the Pacific and Indian Oceans for missions launched from Kennedy Space Center on trajectories that carry the booster far downrange before separation. The landing leg engineering challenge is equally significant. A Falcon 9 first stage has 4 deployable legs that fold against the rocket body during flight and extend outward just before landing. They support approximately 25 metric tons at touchdown, a manageable structural load. The Starship upper stage during the current test campaign performs a completely different landing sequence. A controlled belly flop re-entry using aerodynamic surfaces to slow and orient the vehicle, followed by a dramatic last-second flip to vertical and an engine burn to cushion touchdown. This technique works for ocean splashdowns and will eventually work for Mechazilla tower catches. But for drone ship landings on a moving ocean platform, deployable legs provide precision and stability that catching arms on a ship simply cannot replicate. The legs must be structurally strong enough to support a fully loaded Starship upper stage at landing weight, deployable within the very short time window between the flip to vertical and touchdown, and compact enough when folded not to disrupt the vehicle's aerodynamic behavior during the belly flop re-entry phase. Getting all 3 of those requirements right simultaneously is a genuine engineering challenge at a scale the industry has never attempted before. The Starship Human Landing System provides the most direct window into how SpaceX is solving the leg problem. The HLS variant of Starship, the version that will carry NASA astronauts from lunar orbit to the moon's surface under the Artemis program, must land on legs by definition. There is no Mechazilla on the lunar surface. SpaceX has been actively developing and testing the HLS landing leg system throughout 2025. A drop test at Flight Energies was conducted to verify structural performance and study how the landing feet interact with the lunar regolith, the loose powdery surface material covering the moon. The drop test validated leg deployment mechanics, shock absorption behavior at landing velocity, and the contact interface between the foot and the surface. The landing software, sensor, and radar hardware were simultaneously reviewed and tested. Cold start demonstrations of the Raptor engines in vacuum conditions confirmed reliable ignition after long coasts in space. A lunar landing throttle test verified precise descent rate control during final approach. Every data point from the HLS leg program feeds directly into the engineering of legs for the standard Starship upper stage used in Droneship operations. The moon landing leg and the Droneship leg are not separate programs. They are the same engineering foundation applied to two different landing environments. The FAA's official inclusion of Starship Droneship landings in SpaceX's operational authorization framework is a regulatory milestone that has received far less attention than it deserves. FAA approval for a new landing method is not automatic. It requires exhaustive safety analysis, failure modes for landing a vehicle of Starship's scale on a moving ocean platform, consequences of a landing accident at sea, acoustic and blast overpressure effects of the Raptor landing burn on the ship itself, and maritime traffic risk in the vicinity of Droneship operations. The fact that the FAA has formally acknowledged this operational mode means those analyses have already been conducted and accepted. The regulatory path is open. What remains is completing the hardware. The new large drone ships, the deployable legs on the vehicle, and the software integration between Starship's flight computer and the drone ship's dynamic positioning system that keeps the platform stationary within acceptable tolerances as a 200-ton rocket descends toward it. Now here is the competitive reality that the title of this video directly states. And it is not an exaggeration. No other rocket company in the world is developing anything that combines Starship's payload capacity, its full reusability design, its landing flexibility across tower catches and ocean drone ship landings, and its target launch cost. Rocket Lab is pursuing propulsive landings for its Neutron rocket using a 400-foot landing platform called Return on Investment, expected to debut in 2026. But Neutron is a medium lift vehicle, not remotely in the same payload class as Starship. Blue Origin's New Glenn has flown and demonstrated first-stage reusability with ocean landings on a drone ship, a genuine achievement, but its payload capacity is approximately 1/6 of Starship's. Its reusability architecture does not include the upper stage, and its launch cadence so far cannot approach SpaceX's operational tempo. ULA's Vulcan rocket is an expendable vehicle. Arianespace's Ariane 6 is expendable. China's Long March family is predominantly expendable with limited reusability experiments underway. Russia's Soyuz and Proton are fully expendable. The gap between what SpaceX is building and what the rest of the global launch industry is operating is not a modest technological lead. It is a generational discontinuity. The Falcon 9's drone ship landing history tells the economic story most clearly because it is the proof of what happens when you combine high reusability with high launch cadence over time. SpaceX completed its 400th orbital rocket drone ship landing on August 27, 2025, when the Falcon 9 booster B-1095 touched down on the drone ship. Just read the instructions during the Starlink 10-56 mission. Individual Falcon 9 boosters have now flown more than 20 times each. In 2025, SpaceX planned over 170 launches, a cadence that is only achievable because the hardware comes back, gets inspected, gets refueled, and flies again within days. The cost structure of a launch industry where the rocket is genuinely reusable and the turnaround is measured in days rather than months is fundamentally different from every other launch cost structure that has ever existed. When Starship reaches the same operational maturity, drone ship landings included, both stages recovered and reflown, the economics improve by another order of magnitude beyond what Falcon 9 already achieves today. The two drone ship landing methods, Mechazilla for missions returning to base, and Legs for downrange ocean landings, are not competing approaches. They are complementary systems that together give Starship a recovery capability that no other rocket in history has possessed. Mechazilla enables the fastest possible turnaround for high-frequency operations at fixed launch sites. When the booster returns to the tower, it can be immediately restacked with a new upper stage and prepared for the next flight without leaving the launch complex. Every minute saved in the turnaround cycle is a minute closer to the launch cadence that makes the economics of Starship truly revolutionary. But Mechazilla is geographically fixed. It exists at Starbase in Texas and will eventually exist at Launch Complex 39A at Kennedy Space Center. For every mission that does not have the trajectory to return to those locations, the drone ship fills the gap. With both systems operational, there's essentially no mission profile that forces SpaceX to sacrifice the booster. Every booster comes back, every booster flies again. The only question is whether it comes back to the tower or to the ship. The commercial and government mission implications of drone ship landing capability for Starship go far beyond launch economics. NASA's use of Starship as the Artemis human landing system depends on demonstrating that the vehicle can reliably perform precision landings in environments without fixed infrastructure. The moon landing demonstration uses legs and relies on landing software, sensor systems, and radar hardware that are directly inherited from the drone ship program. SpaceX has confirmed that the HLS test flight program includes a long-duration space mission where 2 starships rendezvous in orbit to conduct the critical in-space propellant transfer needed for deep space missions. Both starships in that test will be equipped with docking ports and Dragon Eye navigation sensors, the same sensors already proven reliable on Dragon crew capsules, to enable autonomous rendezvous and docking. The results of that test, combined with the Droneship leg landing data, will give NASA the confidence that Starship can perform the precision autonomous landings required to put astronauts safely on the lunar surface. The leg design is not just about ocean drone ships, it is about proving that Starship can land precisely anywhere, on Earth's oceans, on the Moon, and eventually on Mars. Looking at the broader competitive landscape one more time with full clarity, the combined effect of Starship's payload capacity, full 2-stage reusability, dual landing capability, spanning tower catches, and drone ship leg landings, in-space refueling capability, and target launch cost below $2 million per flight is not a marginal improvement over existing options. It is a transformation of what is economically possible in space. A single, fully reusable Starship can deliver more payload to low Earth orbit than any rocket currently flying, at a fraction of the cost per kilogram, and with hardware that can be reflown dozens of times. Competitors who are still flying expendable rockets or recovering only the first stage are not falling behind on a linear scale. They are operating in a fundamentally different economic universe. When drone ship landings make Starship's full 2-stage reusability available for every mission profile regardless of trajectory, the competitive gap widens further. The landing legs are one component of one vehicle, but what they represent for the business of launching things to space is the closing of the last major gap in Starship's operational envelope. Mechazilla catches, legs land, upper stage recovers, both stages reflown, any trajectory, any orbit, any distance. When that full envelope closes in the second half of 2026, the rocket industry will be forced to answer a question it has been quietly dreading ever since Flight 5 caught the booster in those tower arms. How do you compete with a machine that does everything, costs almost nothing to fly, and gets better every single flight? The honest answer, for most of the industry, is that you cannot. And the landing legs are the final piece of that answer arriving. The second half of 2026 is when the entire industry is going to see what the next step looks like in practice. It will not be a quiet milestone. When a Starship upper stage descends on its own landing legs onto a drone ship in the middle of the Pacific Ocean for the first time, the significance will be impossible to miss. The first drone ship landing of a Starship upper stage will not just be a technical milestone, it will be the moment that makes clear to every other rocket developer in the world that the operational flexibility of Starship is not limited to missions that happen to end at Starbase. Any trajectory, any orbit, any downrange distance, land the booster on the ship, recover the ship, fly the booster again, repeat. That is what full reusability at Starship's payload class looks like when it reaches operational maturity. No other program in existence is building toward it. No other program in existence has the combination of hardware, regulatory framework, operational experience, and financial backing to realistically get there. The landing legs are not just a technical upgrade to Starship. They are the key that unlocks the full operational envelope of the most capable launch vehicle ever built. And once that key turns, the rocket industry will never look the same again.